Hello there, Mr. Chan here for Algebra 2. I'm about to do lesson 3-1, graphing polynomial functions. When you get a chance, please turn to page 61 of your note taker. So let's get started here. Zoom in a little bit, maybe a little more. Great. So I like to look at this whole chapter as being just about polynomials. I've been joking about the word polynomial for years by drawing a bird. Famous bird named Polly. My dad joke of the day. That's my polynomial. Get it? So the opener here is about these things called polynomials in the form of x to the n power. X to the n power. N is an integer, a positive integer. It could be 1, 2, 3, 4, and so on. This whole chapter is about what they look like, how they behave. That's referring to how they look on the graph. Whether you're going from negative infinity or going to positive infinity, we'll talk more about that later. But the first question looks like what happens if your n power is odd? These are called literally odd functions. In algebra. There are three cases we're going to try to take a look at here. Go ahead and draw some axes. And we'll explore all three of them using Desmos. Let's switch over to Desmos right now. And you can see right now I already have some graphed here on the left. I have x to the first graph. It's just a line, right? That's red right there. What if I change it to x to the third? Oh, look at that. That's actually called a cubic function, power of 3, the blue one. Zoom in a little bit so you can kind of see that. And let's add in one more odd power here, x to the 5th. So you notice something kind of interesting. This particular function from the origin goes up to the right, goes down to the left of the origin. That's a characteristic. Let me draw that on our note taker. Here we go. So we have x to the first. We have x to the third. We call that a cubic function. And we have x to the 5th. Notice all three of these functions occupy quadrants 1 and quadrant 3. Interesting. They all act like this, whether it's x to the 7th, to the 9th, they all look kind of like that. Those are odd functions. What happens if we change the positive integer to a even number? let's take a look at that possibility. They're literally called even functions. We're going to take a look at 3 of them, 2, 4, and 6, and see what happens there. I'm going to switch over to, of course, Desmos to show you that particular scenario. Here we go. So we just did the odd ones, turn those off. Let's do the even ones. Oh, look at that. X squared was purple. X to the 4th is a little kind of flatter at the near the vertex area, and X to the 6 is like that. Let me zoom in so you can kind of see that. All right, they all seem to go through -1, 1 and +1, 1. So that's where they kind of cross with each other. Let's draw that back on our note taker. X squared, X to the 4th, and X to the 6. Notice that the branches are called passes through quadrants 1 and 2. All right, I'm going to move on. This is a great opener. Kind of get used to what these graphs look like. Odd functions, the branches go up to the right and go down to the left from the center. And here, they both go up from the center, these 2 branches, for 2, 4, and 6. All right, I'm going to take the space next to talk about classifications of polynomials. Classifying polynomials. They kind of take their cue from Latin prefixes. Polynomials are basically a bunch of monomials added together. When you put 2 of them together, you get a binomial. If you put 3 of them together, you get a trinomial. So mono means 1 term, bi means 2, tri means 3. These are terms that are added or subtracted together. Some vocabulary that pops up. The degree of a polynomial is mentioned. Actually, I should just say degree of a monomial. Oops. The degree is the actual power. If you have a 1 power, it's called linear. Power of 2 is called quadratic. Power of 3 is cubic. Power of 4 is called quartic. And power of 5 is called quintic. That's all I kind of know. And that's all you'll need for this course. So classification of polynomials might start off with something like this. Here's an example. -4x plus 9 plus 2x cubed. This is a random polynomial that I wrote for you. And they might say, hey, let's go ahead and put this into standard form. They don't come in standard form sometimes. Standard form is where you take each of the terms of a polynomial and rearrange it so the powers are in descending order. Descending means going down. So if I look at these three terms, this is technically a trinomial. Look at all three of them. We have negative 4x, and technically that is to the first power. There's an invisible 1 there. 9 doesn't have a variable next to it. Okay? And of course, plus 2x to the third. So 2x to the third is definitely the largest degree. So I want to put that first, 2x to the third. Minus 4x is next, and plus 9. Just a reminder that 4x has an invisible 1 right there, and technically, excuse me, the 9 is a constant. It does have a variable, but that variable is to the 0 power. It's invisible. That's technically 1. So it's not even written, so to speak. Some more vocabulary. After you put the polynomial in standard form, this particular trinomial, in the first term there's a number in front of the x. That's called the leading coefficient. We all know what coefficients are. This is the one that happens to be the one that's leading. The degree of the polynomial is next. It's technically the highest degree of each monomials. So we had a trinomial here. The powers were 3, 1, and 0. So you just pick the highest number, and that is the degree of the polynomial. You don't add up the individual degrees. You only pick the largest one. So in all this particular problem, 2x to the third minus 4x plus 9 is technically called the third degree because of the power 3. And we call that cubic. Because it has 3 terms, we call it a cubic trinomial. Okay? All right. Let's move on down to the bottom here. Give ourselves some room. We're going to try to fit some more information here. So, early on, you saw how odd functions and even functions are graphed. What we do talk about is how the arms that go from the center to the left or from the center to the right, how they behave. That is called end behavior. End behavior. So there are 4 situations for end behavior. So write kind of small here. A polynomial, technically, let me write this down, generically, is in the form of f of x equals to ax to the n power. We only care about the leading coefficient and the leading term. We don't care about the other stuff when it comes to end behavior. End behavior is referring to how the graph behaves to the left, negative infinity, and to the right, positive infinity, and how it's graphed, whether it's rising or falling, and that's what we're going to explore. Here are your 4 scenarios. Here we go. If your power is odd, 2 things can happen depending on if your leading coefficient is positive or negative. So let's start with positive first. And then we'll switch to negative next. I might as well write out the other scenarios too. What happens if my power is even? We have those 2 scenarios too. The leading coefficient is positive, or the other possibility is what happens if it's negative. So let's write down all these scenarios out. There you are. either odd or even, or positive or negative for the leading coefficients. Let's make note of that. Positive, negative. I like to write it all out sometimes. One chunk at a time. Let's give ourselves some space here. And we're going to draw in a generic coordinate plane for each one, okay? Okay, we already did odd, positive. You know, like x to the first, x to the third. All those will look like this. Rise to the right, fall to the left. The right, in terms of describing that, is positive, left is negative, up is positive, down is positive, negative. So I'm kind of going to write out all four possibilities, but I'm going to do it all equally at the same time. What happens if your leading coefficient is negative? Your multiplier changes all the y values. So that graph is vertically reflected. Will look like something like this. That a value, when it's negative, does a vertical reflection. Okay, so generically that could be like x to the third. That's negative x to the third, so to speak. And it also applies to x to the fifth, x to the seventh, x to the ninth, whatever. They all have a similar end behavior graphs. Okay, so those are the odd ones. Hey, what happens if it's even? Well, we saw with x squared, x to the fourth, and x to the sixth under decimals, they look like this. They both go up from the center for their end behavior. And if your leading coefficient is negative, it does a vertical reflection as well. Bam, like that. Okay? So those are your four scenarios. Now, we're not finished. We have to have a way to describe what happens when you're going left or going right. So when it comes to standardized questions and even this course, I need to write down the verbiage of how this works. So I'm just going to write this down multiple times. Please write it down as I write it. Write with me as I write it down. As your domain goes to the left, the function does this. As your domain goes right, your function, meaning your y value, does this. So I'm going to go ahead and write all those two things on all four scenarios right now to kind of get it ready to be filled in soon. So forgive me, I'm going to be a little quiet here and write this out for all of these. So this is from the middle now. We're describing something called end behavior from the middle, the origin. We're not talking about increasing or decreasing. That's another chapter that's describing how a function operates from left to right. This is from something called end behavior from the middle. I know, it's kind of strange. Hang in there though. I'll give you some little pointers here in a moment. Hang in there. So this is the type of notation you might see on a standardized test. Okay? X is referring to the domain. Yeah? F of X is referring to the range or the Y value. Okay, so from the middle, let's use the first scenario here. When n is odd and a is positive, you have this graph from the middle. When you're going left, as I'm going left now, the graph drops. Make sense? So if I'm going left, my graph goes down, to represent it going down, I need to describe it using infinity or negative infinity. In this case, it's negative infinity. Negative infinity is downward. My y-value is going down. If I'm going to the right of this graph, the graph is going up. If I'm going right, the graph is going up. Make sense? This is all from the center now. So to describe it going up, I put positive infinity. Okay. So once you understand left, right, up, and down using negative and positive infinities, whoa, let's see, yep, it makes sense from there, okay? The roles are reversed when your leading coefficient is negative in the second scenario, all right? So let's describe that. In this second graph, as x goes left, the graph is going up. Up is positive infinity. Give me little cheat sheets here. The other scenario is what happens if the graph is going to the right from center, it's going down. And that takes care of odd functions. Even functions, I'm going to go ahead and finish that off. We got our left, right, for both the positive and negative leading coefficients. And here we go. For the third scenario, the graph from the middle goes up and up for both of them. Up is positive infinity for both of those. Some books call it rising, some books call it falling. Here we can say up or down. We get the idea. And for the last scenario, the end behavior is both falling or going down. All right. Woo, that's just the opener. But we were able to cover a lot of information here. All right, let's move on to the next page. Here we go. Thanks for hanging in there. I think it's going to start going a bit quicker. All right, example 1. We're presented some random polynomials. Looks like number 1a has 4 terms and number 1b has 5 terms. You can tell by separating the terms with the pluses and minuses. It's been a while since you've had Algebra 1, but I tell my Algebra 1 kids to look for the pluses and minuses and that'll separate the terms for you. I am asked to put it in standard form. Let's do that. That means to put the polynomial in descending order by powers. So in the first one we have, out of the 4 terms here, I see a negative 3x to the 4th as being the highest powered term, so I'm going to write that first. Next we have the x to the 3rd, and then 2x is next, and then finally a constant by itself is 6. I might as well do the same thing over here on the right with the 1b, and looks like the highest degree here of each individual monomial is 2x to the 6th, and so on and so forth. So after you put it in descending order, standard form, the rest of the questions are kind of focusing on the characteristics here. What are the leading coefficients? So for the first one, let's go ahead and identify the leading coefficient is -3 right there. And same thing goes for 1b. +2. Next question, they want you to know the degree of the polynomial. So out of the 4 terms in the first example here and the 5 terms in the second one, you pick the highest power. Basically, you look at the first term anyway of the whole thing. This is the main focus for describing the degree here. So the degree here is 4. The degree of the polynomial is 4. And for the second one, the degree of 6. Okay, great. And of course, the last question is how many terms are there? For the first one, of course, we have 4 terms. And the second one, we have 5 terms. And that's it. We're just describing things, all right? Okay. Any questions? Example 2, we're just going to do some more classification. Use the leading coefficient and degree of the polynomial function to determine the end behavior of each graph. In the first page in this lecture today, we described the 4 scenarios, okay? So let's hone in on 2A here. The polynomial is already in descending order. It's in standard form. I'm boxing the highest degree there. The leading coefficient A is positive. Nice. A is positive. And my power, my degree is even. It's an even degree. So if I look at the previous screen here, whoa, even and positive definitely is the 3rd scenario from the previous page. And that's it. I just have to copy that information, knowing it's an even degree and A is positive right there, right here. As x approaches left, as x approaches right, so we have left and right. Remember what it looked like in the previous screen. My graph looks like that. From the center, they're both rising. So the function rises up as it goes left. And it's also rising as the function goes to the right. And there it is. They're both up and up. Pretty easy. Next one. The next polynomial, g of x function, is in standard form. Nice. Look at the leading term there. The leading coefficient is, oh, this time it's negative. Oh no. Dun, 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 dun. This time though, it's not an, it's an odd function. So we have negative and odd. If you scooch on back up to the previous page, odd and negative is the 2nd scenario. So my graph looks like it's that particular type. So I'll do that. This is kind of a great way to remind me what's going on there. And I'm going to go ahead and use the end behavior notation. I promise you, you'll see this again on a standardized test. They love these questions. They'll probably be on your final as well. Okay, so here is a situation where when I'm going left, the function's rising from the middle, going left. So rising, I'm just going to do this, plus infinity. Yeah, that's rising or up. But if I'm going to the right, the function's diving or falling down. So to describe that as negative infinity, okay? All right, that takes care of example 2. Pretty easy, hopefully. Habits of mind questions. How does the leading coefficient help determine the end behavior of an even function? We know even functions look like this. If your leading coefficient is positive, and it gets vertically reflected if your leading coefficient is negative. So that's all. It's a difference between positive and negative leading coefficients. All right. Yay. If it's negative, it's a reflection. Let's move on to example 3. I remember doing this last year and not liking the function itself. I'm going to change the function. Not a fan of that one at all. Let's change it to f of x equals to -1/2 x to the 4th plus 3x squared plus 2. Negative 1/2 x to the fourth plus 3x squared plus 2. Question, make a table of values to identify key features and sketch the graph of the function. Fine. We went ahead and made it an even function. So this is a characteristic. Power of 4 makes it even. The leading coefficient is negative. Uh-oh. That does change the end behavior, doesn't it? And the degree, of course, is 4. Whoops. So I'll write that down, degree of 4. And something that some books mention, but not necessarily this book ahead of time, I'm going to tell you, you notice a lot of these things, these graphs, overall look like snakes. They go up and down, up and down, and up and down. This particular graph, because of the degree of 3, has a certain number of turning points or U-turns. It's kind of an interesting relationship. When you graph this, and let's do that with Desmos here. Here we go. I'm going to switch over to Desmos. Turn off those even functions from earlier. And turn on, look at that. Whoa. Kind of fascinating. It's opening down because of the negative leading coefficient. It's going downward on the end behavior. And you notice something interesting. It has a certain number of U-turns. Starting from the left, it's going up, then it turns. That's one U-turn. Then it goes back down. Then from the center, it goes back up. And then it goes back down. If you count that, that's 3 U-turns. I'm going to go ahead and take this and copy it onto the graph here from our note taker. Here we go. I'm going to copy that. Let's go and adjust our coordinates. So we highlight quadrants 1 and 2. Great. I'll help you out here. It did cross through 0, 2 very prominently. And then it kind of U-turned right about, I don't know, 1.73, 6.5. Now, where am I getting those numbers? I'll show you through Desmos in a minute. But there we go, 1.73 and 6.5. And it's also mirrored over here to negative 1.73, 6.5. The graph itself looks like this. Okay, this is not the best exact drawing from Desmos, but it's pretty close. Let me give you those points. 1.73, 6.5. It's nice to have technology, isn't it? You'll find the max and mins for you, they're called. In fact, they're called relative maxes and relative mins. I mentioned earlier, these functions, these polynomial functions look like snakes. That looks like a snake right there. Sometimes they have a lot of turns. So we know it opens down. I wanted to point out the relationship between the number of turns and the degree of the polynomial. There's 1, 2, and 3 turns there. They're called turning points or U-turns, depending on which book you're on. Okay? Turning points are U-turns. Here's the relationship. The number of U-turns and the degree are related by a power of 1. The number of turns or turning points is equal to the degree minus 1. So 4 is the degree, minus 1 is 3. That's the relationship. Pretty cool, huh? All right. Second part of the example 3 throws in this random question. Find the average rate of change over the interval from 0 to 2. I decided to change that from -2 to 0. Let's change that problem. So -2 is right here, and 0 is right there. We are looking at the window from here to here. Okay. Rate of change is just a fancy word for slope. As it's moving from left to right, what is the slope? This is not necessarily a question that's asked all the time. We'll take care of it. All right. Rise over run, as you know. Rise are the y values. So I'm going to give you a generic function formula, f of b minus f of a. That's just referring to how the y values change. That little triangle I wrote there is called delta y. Delta means change in y. And don't worry about that. That's just what it means. Over the run is just a change in x's. This is the formula that's given to us in this book. They use a's and b's to refer to those values. That's delta x. All right, let's plug the numbers in. It's just basically a formula. F of b minus f of a is referring to the function that I changed to -1/2 x to the 4th plus 3x squared plus 2. It's a lot of work. Hang in there. Wish me luck. Here we go. I'm going to write small here. -1/2 x squared to the 4th, sorry, minus 3x to the 2nd power plus 2 minus the same thing right there. I'm going to put in the interval values, -2 to 0. It's a lot of work, isn't it? That's crazy. All over b minus a. All right. Well, guess what? Through the magic of technology, you clean this all up, you will get 2, because all these zero out right there. See that 2 right there? Minus -8, trust me, plus 12 plus 2 right there inside the second parentheses there, okay? All over 2. This equals to 2 minus 6 over 2. This equals to -4 over 2. This equals to -2. That is the rate of change. Now, I can't eyeball it. It makes sense, right? This particular spot right there in the yellow highlighted region is definitely -2, looks like, approximately. Next page. All right. Number 4 is kind of interesting. Let's put on our detective hats. They're giving us some clues here. Let's go and draw in some axes. We're coming up with a function, a polynomial function based off of clues given to us. Granted, we won't see this every day in our lives, but this is kind of interesting. We're going to sketch a graph from a verbal description, for example. 4, use the information below to sketch a graph of the polynomial function y equals f of x. Here we go. F of x is positive, meaning the y value. This all means the y value on the intervals between -2 and -1. Okay, so what I'm going to do is write down -2, -1, and say that the y value, meaning how its graph is between, it's going to be positive. See how I'm highlighting this part above the x-axis there? my graph will go above the x-axis between -2, -1, and also between 1 and 2. Interesting. So what I'm doing is I'm kind of being a detective. Okay? So that's positive. Right? It's negative between the intervals of -infinity to 2, -1 to 1, and 2 to infinity. Now remember, infinity and negative infinity is referring to what's happening to the left there and what's happening to the right here. So from negative infinity to infinity to -2, it's going to be negative. So it's going to be below. Okay. So that's what our polynomial function, like a snake, it's going to be going through that particular region. Hey, between -1 and 1, it's going to be negative below the x-axis. See how we're fitting everything in? And of course, from 2 to infinity, it's going to be below negative. Okay. Whew. Back to increasing and decreasing. Interesting. It's increasing from the intervals -infinity to -1.5. That's kind of interesting. -1.5 is like right there. And from 1.5, so from 0 to 1.5, okay. There's 0, and 1.5 is right here. I want to zoom in a little more to kind of see things a little better there. There we go. That's probably clearer for you guys. So somehow it's going up, 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 up. Somehow it's increasing. Let me use a different color here. Going from -infinity to -1.5. Somehow it's going this way. And then from 0 to 1.5. Okay. Somehow it's going here to here. Going upward like that. But it's decreasing in the other direction from -1.5 to 0. Oh, these highlighter pens are kind of messing with each other. We literally see yellow and blue making green, and now I'm trying to use green, and that's kind of weird. And then from 1.5 to infinity. Okay, so we already kind of guess what's going to be happening. So I'm going to just go, whoa, whoa, whoops. See, that's not great. I'm going to do that again. Make it a little curvy. Okay, that's not the best, but that's a guesstimate of what this particular function is based off of the clues given to us verbally. I'm going to go ahead and skip example 5 and move on to the last page here. If you guys have any questions on example 4, not too bad, huh? Okay, so we're just going to skip this one and jump to the last page. Here we go. Aha. I'm going to focus on the right column here. We have a graph that's already been placed here based off of this polynomial. X to the 4th plus 2x to the 3rd minus 13x squared minus 14x plus 21. That's a mouthful. Find the following number of terms. Okay, that's easy. Number 5 says number of terms. 1, 2, 3, 4, 5. Interesting. That was easy. Come on. Next question, how about the degree of the polynomial? So if we look at, it's already in standard form, which is really nice. The degree is right there, 4. Nice, that was pretty easy, come on. Next question, they're asking for the leading coefficient. Okay, fine, fine, fine. Looking at my function here, the leading coefficient is 1. So let me put that down as well. Oh my gosh. This last page is nice. And behavior is next. Notice that to the left, it's going up. To the right, it's going up. So let me indicate that for number 8. So they're both going up. This verbiage we need to understand. Let's write that down. As x goes left, as x goes right, left, right, they both go up. the function that is. Very nice. Yay. Oh, number 9 asks for the turning points. The turning points are related to the degree. Since the degree is 4, the number of turning points is 1 less than that. And that's 3 U-turns, okay? X-intercepts. Well, this is a case where you need technology, definitely. You need graphing calculator. Same thing goes for number 11 and number 12. I'm going to go ahead and place them on the actual graph. I'm going to write down C above for both of these. And let's do that. X-intercepts on our graphing calculator, we will eventually find them being, they will cross the x-axis at -4, -2, 1, and 3. I'm going to write that down. I would like to scooch on up to the top there. Here we go. Whoa. And switch over to, of course, Desmos. Technology is very nice. I'm going to switch to the last problem here. Bam. Okay, so right there, you can clearly see it crosses through 4, -2, 0, 1, 0, and 3, 0. So those are your x-intercepts. They want relative mins and max. They're referring to where the turning points are. So if I click on here, look at that. It's -0.5, 27.563 for my relative max. It's called relative because there's multiple sometimes maxes depending on where you are through the curve. And we have 2 relative mins. One is at -3.193, comma -25. We'll probably round that down up. And the other one is at, of course, 2.193, comma -25. Let's go ahead and transfer that information to, of course, our notes, and we'll be done. Yay. Here we go. So this point right here is called a relative max. Whoops. Let's do that again. The whole page kind of shifted on accident there. That max is at approximately -0.5, comma 28-ish. Relative max. Then, of course, the other two are called relative minimums. Let's focus on those two ones. The first one's at -3.2, comma -25.3. It's been rounded. And the other one is at 2.126, comma -25.3. These are the answers I got from my graphing calculator. Desmos was a little off, so these are the ones I actually got from the Casio graphing calculator. These are your relative minimums. All right, that takes care of the lecture. Are there any questions? I know that this was kind of lengthy for the first page, but everything else kind of sailed through. Once you know, get used to the vocabulary, the classifications, but not too bad. Thank you very much. Have a good day.